Okay, fellows, lesson 8 of Big Data Applications Analytics, Jeffrey Fox instructor. And this is discussing data science and the pipeline which runs from data to information to knowledge to wisdom to decisions. That's this pipeline here. And I sometimes denote this whole thing as DIKW, data, information, knowledge, wisdom. Because wisdom is not so clearly defined, but it's sort of intuitively obvious. Wisdom is sort of a community property, whereas knowledge might be the knowledge of an individual. So wisdom is sort of a more sophisticated knowledge. And we also will have a little discussion of how the sort of commercial effectively approaches to data science, the platforms that enable data science and activity. So let's get going. Thank you very much. And that's stated precisely here. And I say under decisions, we have things like community acceptance of results, like the Higgs particle exists. That's an example of physics community wisdom. And another possibility is that the government will run some data through this process and make a decision. We will offer some new healthcare service or something like that. Typically, as you go down this pipeline, the amount of data measured in bits and bytes decreases, it goes down in size, where if you like, the value goes up. So, and that's a very important, that's actually why it's not so easy sometimes to say how much data there is, because people can quote the data at this level or this level. And sometimes the data at this level is actually thrown away immediately because it's produced in some sensor and you immediately process it and then you get less. I mean, if you was a satellite running around Mars or something, where there's a huge cost of data transfer, you would do as much processing possible before you sent the data. So you put it as far forward in this pipeline as you could. Here's a picture which I've used an awful lot, which shows this information, data, information, knowledge, wisdom, decision process in a sort of broad fashion. Around the edges here, we have all the sources of data, or actually of information, or knowledge, including raw sources like these are seismographs. This is probably a bioinformatics machine. Here's some water measurements. And here we have some telescope, a smartphone, or so on. We have just services running on computers. We have satellites. We have just another cloud, another whole thing. Here we have the LHC detector. We have a database. We have a Hadoop cluster. We have a grid. We just have some storage. We have a webcam. We have a telescope. And these are just run through filters. The filters are what promote you through this pipeline. You do not go from information to data in a filter. You go from data to information, information to knowledge. So here we trundle through our various things, data, information, knowledge, wisdom, and then we go to the portal where the president or you or whoever's looking, the doctor, makes the decision. This is how we're going to treat your illness, or whatever the decision is. So this is a generally important picture, and you can say that most of these things are filter clouds running analytics. I also put so-called discovery clouds because you're going to do queries on this data, and that's going to be part of your decision making. And all of these things in principle run on clouds. They're all built as services, and that's the way we're meant to do things this world. And here is our final slide in this set of this very general discussion of the pipeline. And we just take Google Maps and navigation as the example of the field. So the data is the original maps, USGS, satellites for the overlays, and the street cams. The information is the integration of that data we have to clean up on a basic Google Maps web page. Knowledge is when Google Maps displays a particular way to get from place A to place B, sometimes with multiple choices. And then finally, the decision of the wisdom comes when you actually decide what route to drive, and you drive that route, hopefully getting to where you want to go. So this is just a simple example of the DIKW pipeline, which is pretty universal. Although I stress that the actual dividing line between data and information, between information and knowledge and wisdom and decisions is extremely artificial and wishy-washy. So you shouldn't read too much into that. All right, well, we've shown there were lots of hype curves, and there was a hype curve for data science or for advanced analytics and data science, which is just the technology that enables the practice of data science. And well, there are all sorts of things here. Optimization. As again, Spark, we know that's a very popular cloud computing platform. Graph analysis. Natural language question answering. It's pointing out where big data was the year. This was 2015. Big data is here. As I think I mentioned, things like big data and clouds are so important, they've just disappeared off these hype curves. They're no longer hype. They're part of the world. And here we have, there's a lot of important things which underlie the revolution in maps and ride-hailing and things like that, which are geospatial intelligence. Event stream processing. Almost all data comes in events created by accelerators, or people tweeting, or Internet of Things devices doing their thing and telling you the burglars invading your home or whatever it's doing. And here we have languages like R. We have various analytics on video and text, speech analytics, predictive analytics, machine learning. These are all, actually, it's interesting. We'll see next year how Hadoop-based data discovery collapses because of Spark. It's sort of interesting. It was because people would not probably agree with that. Hadoop is superseded by Spark. Hadoop is still actually good at what it does. So that's 2015. Now let's see what happens the following year. 2016. We have Hadoop disappearing in a clunk, bong. Pretty sad. Few things were obsolete before the plateaus. Some just disappeared because they're boring. Grid computing, I think, was a little like that. Others disappeared because they're so important they get absorbed into the ecosystem, like cloud computing and big data. Here's Spark popped over the top. Deep neural nets, we know those are very important. Event stream processing, machine learning, these are all things we work on. And we actually, here's R. It's now become so well established it doesn't require much notice. Python. We would always tend to use Python as a better language than R. Quite by optimization, which is a really venerable. Everything in life is optimization, because all it's like a deep learning network is an optimization. It minimizes some giant mathematical function. Graph analytics, we know that's pretty important. Cognitive computing, that's Watson from IBM. So here we have just lots of nice, nifty little things, reinforcement learning, some sort of interactive guided analytics, and so on. So these are just, they're even just important because they tell you the types of things that at least Gartner considers important for data science. Now let's see the Magic Quadrant, which has IBM at the top. Maybe that's because of Watson. I don't think everybody would agree with that. Microsoft, there's Azure Machine Learning. MathWorks, MathWorks has, MATLAB has capabilities in this area, where, say, R with its huge library of routines, especially in biology, is, and where Python with its important libraries are, I don't know. So I would say this is a slightly biased system. This is for data science platforms. These are the environments you use to do data science, because we don't actually use any of these. because we effectively construct our platforms using workflow and other technologies. One that would appear, actually should have appeared here, is TensorFlow. That's a very popular data science platform these days. So it's cohesive software. Maybe the work we do is incohesive. And it has lots of building blocks which we're putting together to do data science solutions. So here we are. We're going to chase IBM. I'm sure we can do better than them, because Watson doesn't tell you what it does. So that's a serious problem. You can't really do science or make discoveries if you don't know how you're doing. So here's how they judge some data access. How do you get data into the system? Data preparation. We know that cleaning up data is very important. In fact, people often say that takes a good fraction of the time. We want to explore the data in a non-controversial fashion, visualize it. We need to automate lots of things. So we need to press a button and say, discover truth, become wise, make a decision. User interface. Well, that's probably rules out everything we do. That's some nice look and feel. Machine learning. Well, that is in some sense the core analytics. It's not quite clear what isn't machine learning. The simpler types of all statistical analyses, I believe, are not called machine learning. Machine learning is reserved for sophisticated things like clustering, support vector machine, and things like that. And of course, deep learning and dimension reduction, etc., etc. And a few more things. Other advanced analytics. Well, here's what become the statistics. Optimization, I say, it's sort of interesting. Simulation is again, so that's how you build your model. If you describe your data with a model, you need to do a simulation. Text analytics, image analytics, those are, of course, machine learning. Flexibility. Do you buy a universal package like Watson, which does everything in a way you don't understand, or do you have a cleaner thing where you can build it up? Of course, deep learning, I made a little fun of Watson, but other systems have this problem. Just deep learning networks at the point you're not quite certain why they did what they do. Scalability and performance. If you multiply your number of nodes by 10, your product by 10, does the execution time remain constant? Here we want to look at the use of the predictive model markup language. It's a language for specifying models, and we have to, of course, the software and package apps. And here, this is sort of software-defined data science, which is sort of related what we do with a project called Cloud Mesh, which is software-defined systems. And here we need to manage everything. Everything always needs to be managed. But we have to have security, resource management, scheduling, metadata for governance and reuse and version management and so on. You have to have GitHub sitting there to manage the versions of everything you do. All right, so that's data science platform. And here's the last set of data science platform capabilities. You need to be able to have a lot of models and understand the effect. And of course, the role of models is sort of interesting. Though in some sense, data science tries to do as much as it can without models. A deep learning network, it implicitly has a model because the network itself is a model. What you feed into the network is a model, because you can always transform the data. Do you take, let's take an image. Do you feed in the moments of the image, the Fourier transform, or do you feed in the pixels? There's, in some sense, mathematical equivalent, but one might give you a better answer than the other. Does it have solutions, such as how do I see if I'm ill or not? Can I detect fraud automatically? Recommender systems, etc., etc. Anomaly detection. These are just specific machine learning, if you like, outlier detection. Collaboration. Is this system allow multi-user use and integration of their ideas? Coherence. Is it truly a system or just a bag of a toolkit bag? Which, of course, the latter might be the best. because especially today when things are changing so fast, and not so obvious you want a coherent system, but still, if you can provide the same capability coherently as the other person does incoherently, then they certainly like me, then probably should do it coherently. All right, so that's the end of data science, where we had this initial broad discussion of DIKW, which is really a fundamental idea. I remember teaching that. It was my first class when I came to Indiana University in 2001. I taught DIKW, and I still think it's a pretty reasonable thing to teach. So here we are. This is the end of this lesson on data science. Thank you very much.